Let's have some practice adding and subtracting negative numbers. So the first example I want to look at is 2 minus 3. So right now I'm just subtracting a positive number from another positive number, but you might already see that I'm subtracting a larger number from a smaller number, so I'm probably, or I will definitely end up with a negative number. But let's just think about this a little bit, and I'm going to do it with the number line. So there's my number line right over there. Now if this is 0, this is 1, this is 2, this is -1, this is -2. We could view this as starting at 2, so this is 2 right over here, and then we're going to subtract 3 from that 2. So we're going to move 3 to the left on the number line. So we're going to move 3 to the left. 1, 2, 3, and that gets us to -1. This is equal to -1. Now let's mix it up a little bit more. Let's imagine what would happen if we had -2 minus 3. So this was +2 minus 3. Now let's think about -2 minus 3. So once again, let's draw our number line. And I'll put 0 over here. So this is 0, this is 1, this is -1, -2, -3, -4, -5, -6, and I could keep going. But we're starting at -2, and then we're subtracting 3 again. So once again, we're going to move 3 to the left of -2. So we go 1, 2, 3. We end up at -5. So this is -5. So notice in both situations, we subtracted 3. We moved 3 to the left on the number line. It's just here we started 2 to the right of 0. Here we started 2 to the left. 2 to the left of 0. This is -2. Let's do another example with these same numbers. Let's imagine -2 plus 2, or sorry, plus 3. And I encourage you to pause this video and try to think about this on your own. So we draw the number line again. I could draw a straighter number line than that. So draw the number line again, and let's say that this is -2, -1, 0, 1, and 2 again. We're starting at -2. We're starting 2 to the left of 0. So we're starting at -2, and we're going to add 3. So we're going to go 3 to the right now. 1, 2, 3. And we end up at +1. Now let's think about 2. So +2, and we're going to subtract a -3. So we're going to subtract -3. In other videos, we've already talked about this. In fact, there's a video explaining why this actually makes sense. But when you subtract a negative, this is the same thing as adding the positive. So 2 minus -3 is the exact same thing as 2 plus +3. These two statements are equivalent, and this just boils down to this right over here is just going to be 5. Now let's mix it up a little bit more. Let's imagine -2. Let's imagine -2 minus -3. Minus -3. Now this might seem really intimidating. I have all of these negatives in place here, but you just have to remember, subtracting a negative like this is going to get you a positive. So this is the exact same thing as -2 plus 3. And -2 plus 3, we've already seen it right over here. You start at -2. You start 2 to the left of 0. And then we're going to go 3 to the right. We're adding 3. 1, 2, 3.
Counting by systematic listing. And when we have small groups of things, systematic listing is very convenient and it's pretty easy to do. All right, so we're going to consider a group of students, Abigail, Bailey, Nate, David, Elias, and Macy, and we're going to list the different ways of forming the following groups. So, well, let me just read part A. All right, so number 1 says, a president and a treasurer if they are not of the same sex. So let's go back first to make sure everybody's clear. Elias, boy. Although I tell you what, sometimes teachers don't know when they see his name. That's my son. And then Macy, that's girl. All right, so if you take a look, so the first thing is it says a president and a treasurer if they're not of the same sex. So what we're going to do is we're going to actually pick, and we're just going to pick the first person in the list, which would be Abigail, and we're going to let her be the president. So when we write these, we're going to write the president first and the treasurer second. Not because it matters, but because we have to pick something, so we're just going to pick that. Okay? So one option is that I have Abigail be president, and if Abigail is president, who could be treasurer?
Any of the boys.
Any of the boys. So we could have Nate, or we could have Abigail and David, or we could have Abigail and Elias. So these are the three ways that Abigail could be president. Make sense? Okay. But she's not the only one who could be president. Who else could be president? Bailey could be president. And if Bailey's president, who could be treasurer? Nate or David or Elias. Okay, so let's keep going with girl presidents. There's one more girl in my list. It's Macy. So Macy could be president, and if Macy's president, then who could be treasurer? Nate, David, or Elias. Are we all good with that? Okay, but that's just half of them, isn't it? Because I just have the girls as being president so far. Agreed? So I'm going to do the same thing now with all the boy names. So let's start with Nate because he's the first on the list. I could have Nate president. If Nate's president, what are my different options for treasurer? Abigail? There's lots of ways that you could have done this in an organized list. I kind of picked the one that sort of spoke to me when I looked at it and thought about it, right? You may have a list that's organized differently, but here's the kicker. If you don't organize your list, you're probably going to forget somebody in the list. So be organized when you're listing these out, or you will end up missing something or duplicating something because you'll write it twice because you weren't paying attention. Okay, so the goal is an organized list. How many do I have? 18. So there's 18 ways of doing this. I mentioned that because we're going to come back to this in lesson 2 and talk about that.
In this video, we're going to take a look at Venn diagrams and two-way tables and how we can calculate probabilities using these two things. So in this first example, we've got a survey of students who either like maths or don't like maths, or they like English or they don't like English. So they've been asked whether or not they like English and maths, okay? And there's a couple of gaps missing in my table, so I'm going to have to work out how to fill those in. Now, what we need to understand is that in this, across the top here, I've put in like maths and don't like maths. So if I read down here, this box tells me the amount of people who like maths and like English. This one tells me the people that like maths but don't like English. And this tells me, the 33, how many people like maths in total. Okay, so basically this splits the liking maths into two groups. Either they like maths and English, or they like maths and they don't like English. So that means if there's 33 people altogether that like maths, that means there was 5 of them that don't like English as well, because those two numbers have to add to 33. Okay, now this box here is people who don't like maths but like English. So the way I can fill that in is if I read across, my total has to be 61. So all of the people that like English, there's 61 of them, okay? So if 28 of them like English and like maths, then we have to do 61 minus 28 to work out this number here. And so the amount of people who don't like maths are 33, okay? So that's people who don't like maths but like English. Okay, now this number represents the number of people who don't like maths and they don't like English, so they don't really like much. So altogether, this column will tell me that there are 67, so if I add those two together, 33 and 34, 67 people who don't like maths in total. And then this number here tells me the total number of people who don't like English, which is 39. Okay, and this number here is really important because that tells me how many people were in my survey. And those two need to equal 100 and those two need to equal 100. So let's check 61 plus 39, that gives me 100, and 33 plus 37 also gives me 100. Now, okay, now we're going to look at how we might use a Venn diagram to display the same information. In the Venn diagram, I've labeled them M and E, so M for maths. So when we fill in a Venn diagram, we always start with the middle or the intersection of the two circles. So how many people like English and maths? We know that is 28 people. Okay, so over here is how many people just like maths, not English and maths, but just like maths. And that would be this number here, 5 people, because these 5 only like maths, they don't like English. Okay, same case on this side. Now we want the people who only like English, but they don't like maths. So that is this number here. This is the people who, oh, sorry, I'm wrong. It's this one up here. So this is the amount of people that like English, okay, but they don't like maths, so 33. Okay, so that's how we fill in our Venn diagram. Now, because let's take a look at maths here. If I was just looking for the probability of maths, I would need to add these two numbers together because all of these 28 people and all of these 5 people, they all like maths. Okay, so 33 people altogether like maths, and we know that already. Okay, that's what our table told us, so we know we're right. Now we need to somehow account for the people who don't like anything, because in the circles we've only got people who like maths and who like English. So outside here goes the number of people who don't like anything. So they don't like maths or they don't like English. So where can you find that in the table? Okay, that is that number here. These guys here, they don't like maths and they don't like English. So I've got 34 people who don't like English or maths, so they go outside of the circles. Okay, now the way you can check that you got the answer or that you've made the Venn diagram properly is all of these numbers, 5, 28, 33, and 34, they should add up to the total number of people in our survey in this case. So if I add 5 plus 28 plus 33 plus 34, I should get 100 total. So let's just check that. 5 and 28 is 33, plus another 33 is 66, plus 34 equals 100. So I know I've done it right. Okay, so that's how we set up a Venn diagram from a two-way table.
Craig has 5 shirts, 4 pairs of trousers and 6 pairs of socks. Lucky man. How many different combinations of shirts, trousers and socks does he have? Now, it's almost kind of like a logic problem, this. And the actual topic itself's got a couple of names. Strategic listing strategies is one of them. Sounds a bit posh. Product rule for counting is another. I don't know. I just kind of call it combinations. All right. Now, for regular viewers, it'll be no surprise what's about to happen next. I'm going to draw a diagram. Always the best way to approach these questions every single time. Okay. So I can't draw. That's been well established, so no chance of my attempt to draw a shirt. So what I'm going to do instead is I'm going to get a little colour system going here. And I'm just going to deal with the shirts and trousers first. We'll leave the socks for later, because if we can get the answer for the shirts and trousers, the socks will fall into place. Okay, so 5 shirts. I'm going to represent them with 5 blobs. 1, 2, 3, 4, 5. There's me 5 shirts. Now let's get myself 4 pairs of trousers. 1, 2, 3, 4. And the first question I'm going to try and address is, how many different combinations of shirts and trousers can I have? Well, let's think about this logically. Here's my first shirt. I could put that with that pair of trousers. There's 1. Or I could put it with that pair of trousers. There's 2. Or I could put it with that pair of trousers. 3. Or I could put it with that pair of trousers. 4. So I've already got 4 different combos straight away. But who's to say I'm going to wear that first shirt? Instead, I might like the look of this shirt. So I could put this shirt with that pair of trousers, that pair of trousers, that pair of trousers, or that pair of trousers. So I've got another 4. But then again, who's to say I'm a fan of that shirt? Instead, I might decide to choose this third shirt and put it with that pair of trousers, that pair of trousers, that pair of trousers, or that pair of trousers. And this fun continues, because by the time we get to the fourth shirt, oh, hello, my pen would work, that fourth shirt could go with 4 pairs of trousers, and the fifth shirt could go with 4 pairs of trousers. So, and every one of those combinations is completely different. So how many have I got? Well, 4, 8, 12, 16, I've got 20 different combos. So there's 20 different combinations of shirts and trousers. And how did I get that 4? Well, it's 4 times by 5. 4 times by 5 is going to give me the 20. But now, imagine I've got those 20 combinations, and then I've got to start thinking about my pairs of socks. So let's go, imagine my socks are this colour. So I've got 1, 2, 3, 4, 5, 6 pairs of socks. So each of those 20 combinations, so these 20 combinations will be right kind of little things like this. Well, in fact, let me go for a white so you can see. So I've got like now 20 combinations going on, and each one of these 20 could go with 6 pairs of socks. And every one of those would be completely different. So I would end up with 6, and then I'd have another 6, and I'd have another 6, dot, 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 and another 6. How many 6s would I have in total? Well, there'd be 20 sets of them, right? 20 lots of 6. So how many combinations am I going to have? 120 completely different combinations. And that comes from saying I had 5 different shirts, 4 socks, put them together, give me 20. Then each of those 20 has 6 different socks that could come from it. Sorry, 5 shirts, 4 trousers, and 6 different pairs of socks that could come from it. And that's going to give me 120 different possible combinations. So there's my answer. But you know what I'm going to say to you next, right? The fun's just getting started here. Don't leave me now, because let's have a think where some of these wrong answers come from. Where would 26 come from? Well, I think this is a bit unlucky, this. I reckon 26 is somebody who's done this bit. 4 times 5 is 20. They're laughing there. They've got 20. Then they thought, oh, let's just add 6 pairs of socks on the end. No, 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 no. Each of those pairs of socks can go with each of those 20. So there's 20 lots of 6, not 20 plus 6. What about 3? Oh, three's not so good. 3's just saying, well, there's a shirt, trousers, socks, 3 different items, 3 different combos. And 15's a common one, right? 15, you can see that. 5 plus 4 plus 6. There's got to be 15 different combos. But no, we've got to multiply. And we've seen why with this diagram.